All right, ready? So, probability. Ladies, come on. So, probability ranges from 0, which is possible, to 1, which is certain. Very, very few things are completely impossible or completely certain, because there's always that really, really, really tiny chance it may not happen. But 0 to 1 is what your values will always be. They are generally going to be fractions or decimals. Okay, so obviously the 0 to 1 follows there. So you cannot have an answer in probability of more than 1. Okay, so if somehow on some of your calculations you've been doing, you get an answer of something that's more than 1, you have done something wrong. Okay, either you've added when you should be multiplying, you've done whatever. Okay, you've done something wrong. Percentages, obviously, the equivalent would be 0 to 100%. So if there are percentages, obviously it can be more than 1, but you're talking about percentages. Okay. Probability of an event is the number of favourable outcomes divided by the number of possibilities. So, how many times has something happened that you're interested in, the thing that you're looking at, over the number of possibilities that there were. So, the whole numbers 1 to 10 are written on 10 slips of paper, which are then folded and placed in a hat. One slip is removed at random. Find the probability it is a 6. What would the probability be? How many of the slips of paper have a 6 on them? So it's going to be 1. And how many pieces of paper were there? So it's 1 over 10. Yes? At least 8. So what numbers are we thinking if it's at least 8? At least 8. So which numbers are we talking? So tell me what numbers they are. 8, 9, 10, which is how many? 3. So it's 3 out of 10, yes? 12. 0. Nice. Okay, obviously none of the slips of paper have a 0 on them. If you wrote 0 out of 10, it's no major, but let's try and get to the habit. If it is 0, just write 0. Complementary events. Okay, so this is akin to sets of Venn diagrams, in that when something is not happening, it's called complementary. So probabilities, we know they add up to 1. Bless you. So if you are talking about the probability of an event happening, and then the probability of an event not happening, those two probabilities have to add up to 1. Okay. Now you've got to be very careful in the event not happening. Sometimes people make mistakes. So, for example, if they're talking about the probability of someone winning a sports match of some kind, so they say the probability of winning is 0.4, and someone will say that means the probability they lose is 0.6. Why can we not say that? Winning is 0.4, losing is 0.6. Why do you think we cannot say that?
Is there more options?
Yes. What other option is there? You win, you lose, or you tie. Yes. So because there is that other option, you cannot say win, lose. You can say win is 0.4, lose, not win is 0.6. Okay, see the slight difference in the way to word it. So just be careful sometimes that you'll make sure that you take into account all of the possibilities. Don't go into that. Okay, so the probability it will snow on Christmas Day is 0.15. Find the probability it will not snow on Christmas Day. So you're going to do 1 subtract 0.15, which is 0.85. Nice. Okay, so scans. Experimental probability. So sometimes we talk about things and they are based on an experiment. So theoretical probability is what we've been talking about. There are 6 sides to a dice, and so we assume that the dice is fair and so on and so forth. Sometimes we talk about experimental probability, and so we're going to use the actual experiment results to determine our probability. Okay, so a drawing pin, thumbtack, we call it. A drawing pin is thrown in the air 20 times. It lands point up 13 times and point down 7 times. Calculate the experimental probability that a single throw results in the pin landing point up. So, point up, what's the probability it lands point up? Pardon? Nice, 13 16 over 20. Because it landed point up 13 times in our experiment, and there were 20 trials. B. The pin is then thrown 300 times. Work out an estimate for the number of times that the pin will land point down. We're talking about an estimate here, so it's not completely accurate. We don't want to throw this thing 300 times. So what we do is we use this probability. Oh, sorry, now we're talking about point down. Okay. So the probability it was landing point down would be what? 7 over 20. Lovely. So the probability it's point down is 7 over 20, and we've now done this 300 times. So to find the number of times that event's going to happen, or the number of times we expect it to happen, we would do 7 over 20, which is our probability, multiplied by 300. Okay? So as I've said here, expected number, which is what we're talking about here, an estimate of the number of times something is happening. The expected number is probability multiplied by the number of trials. Now, please note, when we get an answer here, I don't know what the answer is. You know what it is? Pardon? 105? Oh gosh, that says 105. Note, my answer is 100. Yeah?
Why is it not that you try to get the 20 to 300?
That's another option. You would get the same answer. Okay, it's just that if it was 232 trials, that's not so easy. Okay, so this probability multiplied by number of trials will always work no matter what, rather than you saying, like, how do I get from 20 to 300 and so on and so forth. Okay. But no, this is a number. Do not write 105 over 300, because that's not your answer. That's a fraction. Okay, so it's 105 times that you would expect this to happen. I see all the time people write this, and you have to mark it wrong, because that is not how many times we expect it to happen. If you wrote the words out of 300, that's very different. Okay, but just writing it as a fraction is incorrect. You happy with the difference? Because this, like if I said to you 20 times, and then I said 20 out of 50, 20 out of 50 is it's a fraction. Like if I said to you I was gonna give you $105, and then I'm going to give you this number of dollars. This is a tiny number because it's a fraction. Yeah, because it isn't. The actual answer itself is a fraction.
So we have to try 105 out of.
Well, 105 times. Or you, and as I say, if you wrote out of 300, in your head you're probably saying what you wanted to say had you written this. And so that's fine, because you're making it clear that it's that number of times out of 300, but it's not, you haven't written it as a fraction. Yeah?
Why would you not multiply the denominator by 300? Because then that's going to be over 300.
Remember, when you're multiplying, this is a whole number, so that's equally 300 over 1. Yeah? So, next one. So sometimes they just give you the words. Sometimes they summarize information or give you the information in a table, and you have to get that information from the table. So the table shows the boys and girls of year 7, 8, and 9 at local school. We all know how to read these. Find the probability that a randomly chosen member of year 8 is a boy. Okay? So we are only talking about choosing a student from year 8. So we have to look at year 8 and say, right, there are 110 people in year 8. So that's going to be my denominator. Ready? So the way they word it is very important. So the year 8 is our number of year 8 is our denominator. We then look to see how many of those are boys, which is 66. So it would be 66 over 110.
You don't simplify, right? Is that where it makes
Oh, no, that's a very good thing. Stop TikToking. probability is the one time you don't have to simplify. Okay, so any other time you deal with fractions, you're expected to simplify. It's not, but just be really, really careful, because it was the worst thing in the world would be is if you had a fraction and you simplified it incorrectly, because once you've done that, you have to lose some marks. So I would just leave it unsimplified. The frustrating thing is a lot of textbooks and questions, they do give you the simplified version, so they're human kind of expressions. Anyway, B, find the probability that a randomly chosen boy is a member of year 8. See how they are slightly different? So find the probability a randomly chosen member of year 8 is a boy. So our year 8 total was our denominator. What's our denominator going to be this time?
208.
208, good, because that's the number of boys that there are, yes? And is a member of year 8? 66. Find the probability that randomly chosen member of the school. Okay, so what is our denominator this time? And a year 8 boy, obviously 66. You haven't gone too crazy with the year 8. Okay, but so this is to show the importance of making sure you're reading the information, reading the question carefully, and that's going to tell you what your denominator is going to be. Okay? Mutually exclusive outcomes. So these are events that indicate if one thing happens, then the others do not. Okay? So rolling a dice, rolling each number would said to be mutually exclusive events. If you roll a 5, you cannot also roll a 1, 2, 3, 4, 5, 4 or 6. Okay? You just can't do it. So in a pack of playing cards, selecting a heart and selecting an ace would not be mutually exclusive. Okay? Because those two events can have some kind of overlap, because there is an ace of hearts. You see the slight difference? So rolling a dice, there is only one number on each, so they're mutually exclusive events. If you say selecting a heart, selecting an ace, they're not mutually exclusive because they can happen at the same time. So if they are mutually exclusive, then if you're trying to find the event that one thing or another happens, so one event or another, you would add the two probabilities. Okay? So or, you add. Independent events. These are events where one outcome does not affect any other. Okay, so tossing a coin and rolling a dice, they've got nothing to do with each other. So it doesn't matter what your result is on one, depending on the other. Okay, so it maybe helps to draw summaries. I think I wanted to write that. Or summarise the options of independent events in a table. Okay, so Janine has two fair spinners. One of them has numbers 1, 2, 3. I think I want to say draw a table. Oh, God love me. I really wasn't paying attention to right now. Okay, Janine has two fair spinners. One of them has numbers 1, 2, 3. The other has numbers 3, 4, 5, 6. Janine spins both spinners and adds the scores together. Draw up a table to show the possible scores. Now, they're not always going to ask you to do that in a question, but often it's a good idea. The kinds of things that we're looking for, or easiest ways to do it, are things like this. So 3, 4, 5, and 6. That's one of my spinners. I've then got 1, 2, and 3 as my other. Okay? Now, I'm going to look at my question to see what they've asked me to do. So it says that Janine spins both spinners and adds the scores together. So in my table, I'm actually going to put those scores added together in the box where they meet. So I'm going to put in this box here 4, because 3 and 1 is 4. 5, 6, 7. 5, 6, 7, 8. 6, 7, 8, 9. And I'm putting those numbers in, as I say, because this question says that we're adding the scores together. Sometimes they'll have one part of the question adding, one part multiplying. So in those cases, you may want to consider just writing or summarising the scores that they've got, okay? Or having two separate tables, either works. Now, having done that, I can see that the green numbers indicates the number of options that I've got. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 options. Okay, so that means that my denominator here is going to be 12 because that's how many possible outcomes there are. Yeah?
I think like 6 twice, would that would count as one possible outcome?
No, and that's the thing, because this is rolling a 3 and a 3, this is rolling a 4 and a 2. So they are different options. Okay, and that's why drawing this table really helps you just determine how many options there are, because sometimes if you try to list them, you may miss some, and you think, oh, I've got 6, so that's one of my options, but it's actually the rolling of the spinners that's important, or how the spinners come up. All right, so B then says work out the probability that Janine's total is 7. So then all we do is we say, right, I can see 7 3 times. Oh, out of a possible 12. Done. Easy peasy. This is all stuff we've done before. Remember it? Okay, if events are independent, then if you want the probability of one event and another, then you would multiply those probabilities together. Okay, so one event and another. So when Laston, that's quite long, isn't it? When Laston drives home from work, he has to pass through 2 sets of traffic lights. The probability the first set will be on red is 0.4. The probability the second set will be on red is 0.3. Calculate the probability that both sets will be on red. So here, I've got the probability that it's red and red. Okay? So the fact that both sets will be on red means we've got the word and. Okay? Now, does the probability of the first light being on red have any influence or effect on the second one being red? No. So it means that they're independent events, which means we multiply those two together. So the first one being on red was 0.4, and then the second one was 0.3. Oh, there's a point up there, but it's way up there. So you would multiply those two together. This is also where sometimes people make boo-boos, in that they say 0.4 times 0.3 is 1.2. Okay, because they forget their rules of multiplying decimals. If you're likely to do that, do it on a calculator, because you know that if you get an answer of 1.2, it's wrong. Okay, it should be 0.12. Okay, because 4 times 3 is 12, but we've got 2 digits after the decimal point, so we need 2 digits after the decimal point in the answer. And B, calculate the probability that neither set will be on red. Well, you've got options here. You can either say the probability if it's not red, and the probability if it's not red. So that would obviously be 0.6 multiplied by 0.7, which is 0.42. Well, that's it. Actually, shut up. Okay. Why do those two not add up to 1? Yeah, you've got other options. Yes, you've got some. One of them might be on red, the other may not. Okay. Do I stop there and then we do the rest next lesson?